if you solved it, like, was it difficult? How much time probably it took you? Like, was it a fast solution, or it was just pure concentration and like maybe half an hour of your time? I can see just one answer at the moment at the chat. So who at least tried to solve this problem, just to realize? So there was a problem stated. I need just to realize like how many of you are familiar with this problem um, at the moment, at the second. Okay. Some of you send me answers to WhatsApp and some of you on this chat. So probably I should check both. Mhm. Okay. So most of you solved it, but as I can see, there would be a classical question or classical issue: how to explain um, such matters, how to explain the intuition which happens behind the solution um, of such problem. Sorry, dog is barking. To calm it down. So let's consider the solution. So we have uh, one of them. So probably I will again try to tell you a bit more uh, strategic things. For some of you, it may be some obvious uh, order of things to happen. For others, it may sound as a sort of strategy, how to attack such problems. So first, of course, you read, understand, and here some tips may be added following what we discussed in the first classes. So if we have any issues with reading and understanding such problem, then, and it may happen actually because combinatorial geometry would be one of the disciplines with quite twisted tasks sometimes. Like the text of the tasks sometimes is very tangled. Like you will need to put extra attention to the process of reading and understanding what's happening there. So always a good drawing would be helpful, and also understanding what would be the objects of the situation, what properties do they have, what type of an object is each particular object, and finally, what are the relations? Because combinatorial geometry is mostly about the relations. But we discussed all these stages, so we first read and understand. Then experiments follow. It's almost not possible to do, like, experiments here would be something related to drawings. Again, as geometry, it would be very visual area. So when I see that somebody tries to do geometry solely in his head, I think the person normally is exaggerating his own abilities. Like me personally, I knew probably one person who can do such things in head, solely, I mean. So of course, there would be some moments when you think solely in your head, just in your head. But when that is normally happening when you have a good enough drawing and you drew several drawings already, so you found some extra limitations, and you are in the middle of the process of transiting from one picture to, for example, constructing some other picture and so on. There are legends about those who can do that in their head. I know about one such person in the first half of 20th century. He was blind. So you can imagine like what stage of uniqueness, what level of uniqueness is that situation. So he was forced to do it like that. And I know, not personally, another guy who was Olympiad guy, who just somehow could transfer geometrical information to some algebraic point of view on the fly. So he was mainly transiting to algebra when doing geometry. So I have no idea how was he doing combinatorial geometry, because algebra normally helps not that much in combinatorial geometry. So like drawing for, I would say, normal Olympians, those who are competitors on Olympiads, drawings would be very, very crucial. And you need the experiments because you need to have some at least temporary working version of an answer. Because normally, if you don't have an answer in the problem, you cannot choose the strategy properly. If you have no answer, so far, trying attacking from different oftentimes contradicting to each other sides. So for example, here it would be problem about is something possible? So basically two main answers are possible here? Yes, no. It is possible, it's not possible. So if you don't have the answer so far, like your idea about answer, then you just try both answers in turns. You first spend like 5-10 minutes proving in one direction, then you spend 5-10 minutes proving in other direction. Even if you have some particular idea of an answer, but you don't have quite good argument for that, then still it may be a very good idea trying to alternate your point of view. You try proving one point of view, but then you switch to proving the opposite. How it's done? It's done by proof by contradiction, of course. So you may switch always to this idea of proving by contradiction. So alternating direct proof steps versus proof by contradiction. Why did I mention these things? Because if not mentioning these things, which may look very general, every proof, almost every proof of combinatorial geometric problem may look like a bit of magic. Suddenly, out of nowhere, we take some construction. Suddenly, out of nowhere, we take an answer and say that, okay, let's consider this answer. And, or for example, let's consider contrary to this answer. Of course, that cannot appear just from nowhere, all of a sudden. And that is not how the solution is created, right? So you may notice that I'm always concerned with how a solution would be created by you, not how you will understand the solution, because you are training not to listen the solutions, right? You are training for coming up to new solutions of some difficult problems. And that should be your primary concern. So I know that some students sometimes would be concerned, like if they heard enough solutions of like in some particular topic, was that enough or not enough? But actually, your main concern should be the set of practices which sort of masters do use in that particular area. So notice how do they argue, how do they reason their thought, how they express their ideas in that particular area. So here, if we try to find such construction, we normally fail. Now it's easier to me to speculate on that because I know the answer, right? I know that the answer is it's impossible. So I just understand that normally we wouldn't succeed. But still, I saw several solutions of these problems where students say that they did the problem. So that is why I say normally, because oftentimes we have not perfect drawings, we have some mistakes sometimes. So that is why it refers namely to practice, not to mathematical studies, this part. This is a result of experimenting. Um, and normally fail. And then we'll be in need to prove that something is impossible. So we want to prove something is impossible, or some construction doesn't exist. So if we need to prove that something is not existing or is not possible, I mentioned this. We normally focus on proof by contradiction. Why is that? Because again, as I mentioned when we discussed objects, this division into objects, properties, and relations, the way how our thought is developed normally, how it's shaped by the real world tasks with our genuine experience in cognitive operations, like in the real physical world. We deal with the objects which exist, and we have not that much experience with objects which doesn't exist, right? So we do change the situation by imagining that the object exists. So here we must imagine that the covering exists. So like so we suppose the covering exists, and then when we assumed this, then we can study the properties. And this, quite unexpectedly, this becomes almost like blocking obstacle for most of those who try to solve this problem. They just don't come to prove by contradiction. And they try to study something on the picture, imagining not like I cannot even explain this. So there would be so many ways how to do something in improper way. So that would be the reason. So if you do something properly, oftentimes you have results. Then we consider these two triangles, T1 and T2. And then this suggests some particular position of those, right? And that is how our attempts, they continue with some very particular realization. So we understand that um, we understand that the drawing wouldn't be perfect. We have some I would say draft drawings, and then we try to notice some particular observations. So here we formulate patterns. And that is probably the crucial moment for those who can do mathematics already, who has some preparation in this formal mathematical part, in doing proofs and all these things, but still who is not very prepared in combinatorial geometry. People try to solve problem instead of advance in the problem. I would mention that in big science, in big mathematics, combinatorial geometry would be one of the most emerging disciplines during the last century, probably, during the last at least 30 years. So the previous 30 years would be mathematics would be mostly developing in several areas. Combinatorial geometry would be one of these areas. And that is because it would be related to some applications, right? To the questions of optimal positioning or like sufficiently good positioning of some objects. Um, so um, so we normally, if we have this sensation that we realize something, normally, especially if we can replicate our experience, like the results of what we do, this sensation so you redo that, refine through experience. Like we cannot speculate on our sensations when we try to give mathematical proof, right? It's absolutely not rightful. But that doesn't mean that it's worthless. Normally, like if somebody has any doubts about your sensations and intuition and all these things in the meaning of dealing with some ideas, right? Not intuition that like something is predetermined or not predetermined or like these things. These things we don't touch. Like esoteric understanding of these words, please like leave them outside of this discussion. But what here I name by sensation of something is that like it's almost like your idea, your personal idea that you noticed something, right? We can reformulate that. Intuition that something should be in some particular way. In this context would be that your strong belief, or at least some degree of belief, that the correct solution goes in some particular direction, involves some particular nodes, and so on. So that would be some casual words for describing some cognitive activity, right? I use them in this meaning. So if you have this sensation, or in other words, like you have these words, or at some level you have this inside of your cognition, then we don't rely again just on these words and on some like sensations. We go to the origins, and we go to the material of the topic. We redo and redo and redo our attempts in the problem. So we refine what we notice. And then if we still have this idea that we've noticed something, we must gain the ability to formulate what exactly we notice. Formulate that. In the language of facts. What is in the language of facts? Again, we come to that scheme that we have objects, properties, and relations. Like if you ever had troubles with understanding how to properly prove combinatorial geometry, please be very attentive here. This may sound very general, probably applicable to some other areas, but in reality, that would be at the very core of what we do when we do combinatorial geometry as mathematics, not as hobby where you have no obligations in the form how you do that, in the results, like you can do the problem, you can not do the problem, right? That would be hobby. When you do mathematics or whatever you do for leisure, because you like it, because you just want to be in the process. If you want to come to professional position to something, then sometimes you have schemes, you have instructions how to do that efficiently and professionally, right? So this would be sort of professional instruction in combinatorial geometry. So like not just in combinatorial geometry, it would be applicable to other areas, but in combinatorial geometry, that would be one of the most crucial moments. I see a couple of questions. I will answer a bit later, right? Like I want to finish this first, and then I answer. So we formulate what I mean by language of facts. For example, you say that these two objects, they always do intersect, and like that would be observation about two particular objects and their relation, right? That they do intersect. And when you formulate that in the language of facts, that notice which you did, sometimes you get to something you can prove, and that is how you seek for advances in that area. So here you must be looking for advances in the situation, but not for the solution, because oftentimes looking for a solution would be almost impossible in a difficult problem. That would be sort of a fact. So if you do really difficult problem, probably an open one, you just cannot hope that you definitely will solve it. So if you work in paradigm of solving, then in such case, if you cannot solve, you sort of have nothing, right? That would be all or nothing position. But if you are professional, you also want the intermediate points on the Olympiad, right? Or on some event like examination, whatever, conference, and some informal points. So you try doing advances. And here, like going to the end of the problem here, of course, this problem would be explained normally. The solution of just this problem would be rather short. It's just a particular example of a problem on which we discuss all these notices about the process. So here we can notice that we experience something like it's not enough to cover that triangle with two smaller triangles in some sense, right? So here we have this not formal understanding first. No, would be slide right after this. So here, informally, it's not enough for it's not enough. These two triangles to cover the large triangle. And then if we do this notice, so this idea, it comes from our experience. We try doing that, and that's not like the shape is very tricky. We cannot fit the shape of one to shape of another, or it's not like we have some gaps, we have some holes which are incompatible with covering. And I'm more than sure that there would be many other possibilities in principle what may have happened here. But it didn't, because we had this particular situation. So we have some particular intuition. If we think that we understand something, we normally have some particular intuition about the situation if we did enough pictures, if we did enough experiments. That is why I keep repeating that do the drawings, please do the drawings. And that is, funny enough, that's one of the biggest troubles with students not doing geometry and not doing combinatorial geometry. They just don't have enough drawings. And as to me, that sounds quite funny and sad simultaneously, because like if it's enough just to draw several drawings so that you with a good chance will be granted with at least several points for advances in the problem, like why not doing that, right? So like, of course, you may be concerned with how to do the problem completely, but hey, just make sure that you earn at least some points for that problem. So here, coming again to the process of solving this problem, we have this idea emerging that it's not enough, these two triangles, and then we try studying what exactly is not enough. So this would be something which we may observe as bottleneck. Some very tight part of the conditions, which work as both as obstacle, something which prevents from some other effects, but also it serves as some support. So if you find such argument or such I don't know such part of the problem of the construction, you can push the situation by this particular area, by this point. You use it as a lever to shift this stone of this problem. So what exactly is not enough? Is that area? Probably not, because we can take two triangles of almost same size as the largest triangle, smaller just by small amount, and still it would be not possible to do. Is it perimeter in some sense, or what it may be? Some particular elements. And that is how we unfold this idea. Not enough, then not enough in which sense? And that is how we can come to this final thing, vertices. So here, working with vertices help much, because I don't know other sorts of other solutions. We can notice that we cover just two vertices all the time. And that is how we can come to a finding that one triangle covers not more than one vertex. And now we can prove this strictly, like why it covers not more than one. So proving such combinatorial inequality, like inequality on some construction, it also is something like it cannot prove two and more, right? So that may be a quite good strategy, especially if we deal with positive integer numbers, with quantities. Then we get extra, I don't know, we have a gap in the numbers then. So we either prove directly something about one, but still it most likely would be proof that this part is possible. But then in the most of situations, we must show that for more than this amount, it's impossible to do something. And then we go to proof by contradiction again, because it's about something about impossible constructions, not existing constructions. So we imagine if not, then we have that there are two vertices which are covered with the same triangle, small triangle. And then that triangle has 2 points at the distance, like this unit distance, while that unit distance is more than the length of the side of that triangle. And then we apply famous fact, which we can prove here separately if we don't know it as general statement. We can prove, we can use statement that the diameter for a polygon is realized on one of its diagonals or sides. So in other words, the diameter, or in other words, the maximal distance between 2 points of a figure. So the diameter of a polygon finite polygon, but not necessarily convex, it would be realized on some particular pair of vertices. But in triangle, we have three vertices. All the distances would be same, like maximal distances would be same. So the diameter of right triangle, not right, but equilateral triangle, is just the side length of the triangle. So this statement then becomes not possible, right? Like it becomes like the opposite becomes impossible, like that, which finishes the proof. Yeah. Now we can speak of different types of combinatorially geometric problems. And I had a question about coverings. So covering is normally following situation. So when we have a figure and we have some set of other figures and we need to cover the entire thing. So normally here overlappings would be allowed. Overlaps are allowed if not specified other. So this would be coverings. So we must cover the entire thing. Sometimes we cannot rotate the objects with which we do cover things. Sometimes we can rotate them. There may be different interpretations. Then there would be packings. We have some bigger object and we must fill it with some other objects without their intersection. They normally may touch, but they cannot intersect. And sometimes there would be more special cases. For example, tilings. Those would be normally having signs of both of packing and covering. So that would be filling something without overlaps. So we can say that that is covering plus tiling. Like in some sense, like that we cover the plane, for example, and we tile the, sorry, and covering plus packing. Also, there would be very widespread types of combinatorial geometric problems, which would be regarding some properties of organization the data. So here, for example, we may be considering so-called transversal number. So having this this combination of squares, we may be interested in. I don't remember if I ever heard that in English in this form. Like we normally formulate that minimal number or sufficient number of nails to pick the figures, all the figures. Maybe not to pick, to clip. Like you can imagine when you just take several nails and you like put them through all the objects which are contained in this point. And the idea is that we do clip this as some stickers to a board with these nails or clips or whatever. So these oftentimes would be known as transversal number. But also it would be sometimes known as some informal title, with some informal title like nailing number, clipping number, or whatever. Like I know this in a scientific way as transversal number. And it also sometimes have several other informal titles specific to language. So let's have a break for several minutes, for maybe like 4-5 minutes, and then we continue with what is famous as Helly's theorem. Helly's theorem. I always confuse from the first glance, from the first notice, Helly something and whole something. One of them is theorem, another is lemma. One of them is combinatorial geometric, another is pure combinatoric. So like sometimes it takes time to correspond what is corresponding to what. So Helly's theorem, that is what we'll study. And it's written like this. And you please write to the chat if you know what's that, if you, and also if you ever used it for proving something. And now we have break for like 4-5 minutes. Okay, we continue now, and still I haven't heard from you, like if you ever used Helly's theorem, and also like if you know Helly's theorem. For those who know this theorem, I would suggest solving the problem, like solving now the problem. If you like, the following would be a bit boring for you, like because you know. Uh, Try following problem. Prove. No, like um, a set of convex pentagons with vertices being a subset, no, of a seven gone. Don't remember how to say that properly. Like septagon, maybe. Being a subset of a seven gone convex. Seven gone is considered. Prove all they have a common point. So we have convex seven gone, and we have convex pentagons with vertices being for each of these pentagons being just extracted from the set of vertices of the initial seven gone. So prove that all they have nailing number one, like prove that this set could be clipped with just one nail. And now we discuss Helly's theorem. So Helly's theorem sounds like this. Let me just check that I type it correctly. Yeah. So Helly's theorem sounds in the following way. There are some generalizations and some similar statements, but the original Helly's theorem would be following. A finite set of convex figures on plane is given so that any three of them have a common point, or in other words, could be clipped with one point. Have a common point. Prove all of them have a common point. So this problem would be looking like following. So we have convex figures. And what is convexity? We should now double check. So they do intersect in groups somehow. And it turns out that for the groups of 3, we can notice or formulate that their intersection is quite special. They have all a common point. And it turns out that this picture, for example, is then, sorry, impossible, because it should be a rather more tight construction. So normally this is proved by induction. I wouldn't give you this as home task. I will tell this the proof now. By induction. But what I want to give you to think about right now would be the base case. So here, the statement of this problem makes no sense with n, the amount of figures, less than 3. So if we have 2 or 1, we have no, like especially if we have 2, we have no such triples of figures. So we have nothing to check if all of them have common point. That means that for n equal to 2, we can have disjoint set. So we can have quite special and not regular situation, dislike others. So that's why probably we shouldn't consider n equal to 2 in the same line of cases as the main case of the problem. So induction makes sense starting from n equal to 2. Or n number of figures and at least 3. Then the very base case, n equal to 3, probably isn't worthwhile even asking. Like it is quite crucial to write it down or mention it when you write a solution, because you must comply with mathematical procedures, right? So if the problem is stated for n starting from 3, then you must have something about n equal to 3 in your paper. Because what? Because speaking professionally, just written things would be graded. Just what is written in your paper, what is written of your work, would be graded on a competition, on examination, in your thesis, I mean PhD thesis, somewhat later. Just written thing would be graded or marked. So you shouldn't lose the case n equal to 3. But just recalling it is more or less enough to cover the situation, because we have it in the task, right? But for n equal to 4, so starting from n equal to 4, we have some non-trivial situations. And it turns out that n equal to 4 becomes maybe the most crucial case. So have a couple of minutes, maybe 2-3 minutes, to think about this case if you don't know. If you know, then try recalling the solution of Helly's theorem. If you know the solution, then please try proving this problem. If you know this problem already solved this problem, let me know on WhatsApp. I will write you, I will give you another task, another problem. Okay. Um, let's do this now because I want to give you the solution during the class. So what would be the formulation of the problem for n equal to 4? We will have 4 figures, right? And we have some intersections. And we want to prove that they don't have the common intersection. So we will not discuss this on the picture because too many pictures would be possible, but instead we do an auxiliary construction. So let the figures be figure 1, figure 2, and so on, figure 4. And in common case, in general case, probably F1, F2, and so on, Fn. Then any three have a common point by the statement. So let Pi be intersection of F1 and so on. So every single of them with Fi excluded. Oftentimes it would be denoted like this. So of course, F1 could be also excluded of the intersection of all of them. So P1 would be then F2 intersected with like belonging to intersection. So this would be not intersection, but it would be point. Mm, let's choose such points. And then we have some more reasonable diagram. No, sorry, I didn't mention convexity. So before making the proof, let's revisit property of convexity. So if we have a figure, it's called convex. Figure in plane, body in space, is convex if with a figure F is convex, if with any two its points A and B, it also contains the entire segment AB. So here would be A, here would be B. This would be definition 1. And definition 2, which will go to a home task as a statement to prove, would be another sort of definition of convexity. but it would be mostly used for polygons. Consider a set of points S. It's not necessarily finite, but we can deal with this better if it's finite. For example, if it may be set of vertices, a set of points S, then the convex hull of such set is a set H consisting of all points which could be written in the form alpha 1 P1 plus alpha 2 P2 and so on till alpha K PK, where P sub I belong to S, alpha I would be real numbers which are non-negative, and sum of the numbers would be equal to 1. So from point of view of this definition, convex figure is like a figure is convex figure if it could be represented as convex hull of some set. But the most useful application of this definition would be for convex polygons and polytopes. And the first would be more widespread. So here you may study that this would be namely a description of any point of the inside of polygon with vertices P1, P2, and Pk, or even the vertices of the convex hull of these points. This would be a sort of recursive usage of this definition. But we wouldn't discuss this much, so we will be using the first one. So we can notice that this means some very particular thing about the figure. So in all the directions, it looks, how to say that, like it looks, I would say informally, it looks fat in all the directions. So it's like curvy to outside for in all possible possibility, like in all possible positions. But what is good in, or what is useful with these definitions is that we can prove then that intersection of any two convex figures is also convex. And that is what we'll need for the proof here. So we consider these 4 points, and we have several opportunities how these 4 points may be located on the plane. So as all these 4 objects, they are, I would say, in the same relation to each other. I mean, a priori, we have no special ideas what is closer to what. Then we may say that we have, like, if they form vertices of quadrilateral, of convex quadrilateral, we may consider such numbering of the points that they go in this order. And then if we consider this quadrilateral, it have diagonals, and the diagonals have intersection point. So here, if they form a quadrilateral, but then what we can say, P1 belongs to F2, F3, F4 by definition. P3 belongs to F1, F2, F4, right? Exactly without these indices. But then we can notice that P2 and P4 would be met in both of them. So we can say that these two guys, they belong to F2 intersected with F4. So P1 belongs to F2 intersected with F4, and P2 belongs to F2 intersected to F4, but F2 intersected with F4 would be convex by that lemma. Right? And as it's convex, that means that so entire P1, P2 belong to that F2 intersected with F4, which is exactly what I drew here. So this segment belongs to this. But then we can imagine that this belongs to F1 intersected with F3 similarly, right? But these two diagonals, they have common point, because that is why we consider reordering of the numbers of the indices if we need it, so that we refer to the diagonal correctly. If it was some different numbering, not in the right order, 1, 2, 3, 4, we just take such two indices that this is diagonal and this is diagonal, and that's it. But then we can see that, control that. So the intersection point X belongs to Fi for any I. And so we found the point. Several things remain to be done. First of all, it's not granted that we have a a quadrilateral, it may be triangle as well, but then some point is inside, and please check that this point could be considered as the intersection point for all of them. So this would be PI, then PI is the common point. Again, from convexity. So you check that it is true, but it would be even more simple than this. 3 would be that there would be a segment on which these 4 vertices, 4 points belong. Then we also have a common point. This, please check yourself. Case PI belong to segment. And finally, there is an opportunity that all they coincide, but then we have nothing to prove. So this would be proof of the base case, but funny enough, it could be almost immediately converted into proof of the general case. You just formulate the general case. We'll be proving that each k of them have common point. And then the induction will work starting from from k equal to 3. Then we should prove that each 4 have common point, but we technically done that. So we can now say that any 4 figures have common point. But then the induction should be conducted in such a way that we then have the next case for k equal to 5, so that each 5 of them have common point. But the proof would be mimicking, or in some interpretations, they would be just using, namely this thing, the proof of case n equal to 4. And that is how the induction should be finished. Like actually the time finished, but I wanted to mention one more thing, give a hint for difficult geometry. So if you have any questions now, please feel free to tell or to ask on WhatsApp, and I'll be simultaneously drawing a picture for problem number 9 from the previous task. So any questions? No questions. Okay. No, at least so far. So the previous problem, or not previous, but the problem number 9 from the previous task is, like, as to me, it's very intriguing. So first of all, I don't know any reasonable conditions how to understand that the circles which we draw, they really are in that position which we need. But the picture must look like this, more or less. A, B, C, and from continuity of the circles, if we, for example, change the radius and move the center continuously, then we have a sort of continuous change of the circle. So this helps us to understand that there must be at least one such position for any triangle. But not much beyond that. So we have this situation. I will just give you a hint now. So we do start the problem from drawing this, but drawing this picture may be quite troublesome because we have these things like these segments being not diagonal. So of course, this line from A to A prime, it's not sorry, not diagonal, but not bisector of the angle. Otherwise, there would be no problem in this. But the thing is that those would be completely different segments. So what we do, we actually consider the bisectors, and those bisectors, they do pass through the centers of the circles. And also, they do pass through the in-center of the entire triangle. So this would be IA, IB, IC. So if we do the drawing properly, and now I'm just speculating on what to draw here, right? So if I put all the elements of the task here and seeing that we have circles which are touching something and touching each other, I just draw the centers as well. And I also draw the center lines here. And also, I would be naturally drawing the radii here, because also touching is happening. So putting these radii to the tangency points would be something which we do very frequently. Just one sec. Yeah, so the idea here is like, well, how to prove this by masses. But how we can try to approach this? If the masses would be grouped somehow so that we can group them first along the line A prime, then regrouping so that it is again on B prime, and then on C prime, then it would be probably the victory. Like we will prove then that they do intersect. As we saw, the possibility of putting or introducing such masses is equivalent to the situation that three segments intersect inside of a triangle. But how to do that? How to approach these points in principle? The only thing which is observable so far about the points is that they would be tangency points of the circles, or in other words, the intersection of the center lines with the circles. But we can perfectly use these actually. So we can try to organize the masses so that we do regroup masses into masses in this vertex, and this vertex, and then adjusting the masses so that the mass center of these two, or gravity center of these two, is exactly this point. And then we will have the mass on this segment, A1. And then we'll be looking for such a regrouping of these masses so that the mass is in the point B and in these two centers, and with the same continuation. And if we succeed in doing that, that would be already some plan to introducing masses here so that we prove that property of intersecting all these segments. But now, if we do following, if we do if we put some, like how we combine masses here in vertices and in the centers. we can put some masses to the in center and to the vertices, and then we can group masses in center and in vertices into these centers, and the remaining weight is in the vertex. So that's it. Like, this is the hint, this is the plan, and this is like half of the solution actually. Okay, if no more questions, then we stop now.
I just have a small question.
Yep.
In the previous question, when you say that the pentagons share the vertices as a subset of the septagon, does that mean that the vertices of the pentagon are the same vertices of the septagon?
That is exactly how it was formulated. Like, we didn't say that the pentagons are subsets of hexagons. We said that the vertices of pentagon are a subset of vertices of sevengon.
Okay, thank you.
So the vertices are subset of yeah. I said it in words, but I wrote it incorrectly. So yeah, very right question. All vertices being a subset of vertices of a convex sevengon. Okay, then. That's it for today. Have a good weekend and see you next time.
Thank you.
Bye.
بعد عطل الميتنج خلص.
الله موجود.
اه
خلصان مش مشكلة، نقدر نحكي وبعدين
ريكوردينج
بينزلوه.
شغال.